Hi.
Hey there.
Hello.
Hello.
Hi. Hello.
Yeah, we still have 2 more minutes to get prepared. Grab a seat, grab a coffee.
I think streaming hasn't started yet on this room.
Streaming on YouTube.
I think
no,
I
it
see
is.
it.
Okay.
Yeah. So maybe just as a introduction to the session, we are there's also this Riot chat or Element chat. So the idea would be that those that give the presentation, they switch on the camera if they like, but at least you need to switch on the microphone so that people can hear you. You will get you will be the presenter, so you will have you can then change the slides here and go in your own pace, but well, stick to the time. You have 12 minutes. And afterwards, we have 8 minutes discussion session. I like to not call it Q&A. It's more a feedback session, open discussion. And in order to let the people raise questions and give feedback, I suggest that here on the left side, you have the public chat. So when you listen to a talk, you can either you formulate your question, and then I just read it out later on. Or what's even preferred is that you kind of say that you want to have a question, and then you will be able then to ask the question in live. So unmute yourself then and ask the question. In addition, we have the this chat going on. Again, the links are all on the website. So for those people who follow us via the live stream, they can phrase the question here in this chat. Let me show you the chat just quickly. So here, that's the Element channel, formerly called Riot, and here we have the chat room for this room, and you can phrase your question here. Okay, we're also recording, and we can start now. So first, I'm going to stop my sharing. I just activate the presentation. I make you a presenter, Selman. And yeah, with this, I hand over to our first talk from Selman. He was doing this work completely remote, as I was informed. So really much fits the topic of this conference as well, to work from home. And so it's an open source implementation of the ECSS PUS service, Packet Utilization Service, which is used all over in ESA to control the satellite, so to send commands and to receive telemetry. So I don't know if many of you are familiar with this PUS service, but if you would talk to anyone working at ESA, that's like the daily language, yeah. And he implemented this using the Rust language that personally I'm not so familiar with, and I'm looking forward that you, Selman, convince us of switching to Rust and dropping Python and C and whatever language. Okay, so over to you.
I was convinced when I finished this project. Not finished, finished working on this project for this summer. Is this slide the updated slide I sent you, Arthur? Because I updated the slides. So.
Yes, this is the updated slide.
Okay, thank you. Hello, everyone. Welcome. This is an open source implementation of ECSS PUS services in Rust. Here I will just explain every term briefly. We will talk about a system programming language called Rust, ECSS PUS, which is a standard, and open source ECSS PUS implementation in Rust, which we call Prust, and Prust use cases in VST 104, which was where Prust was deployed first. About PUS-C, ECSS is a cooperative effort for the purpose of developing and maintaining common standards. Its recent iteration PUS-C was published in 2016, and it's relatively new. Prust satisfies some of the service requirements of PUS-C, and PUS is the standard of choice by ESA, and only one spacecraft operated by ESA doesn't use PUS. Here's the VST 104 I was talking about. This board hosts a single redundant onboard computer designed to fulfill the space industry requirements. The main processing unit is STM32L496 96 microprocessor, and this runs the Prust software. Will be presented tomorrow by my co-author Philip Gabe in the title of an open source onboard computer platform for CubeSats. Here, let's talk about the Rust language. It's a programming language focused on performance, safety, and especially safe concurrency. Rust provides memory safety without using garbage collection, but instead through the use of borrow chicken system. And it was choose the most loved programming language in Stack Overflow survey every year since 2016, and I can say I was one of them. Here, why Rust? C remained the only alternative for a long time in embedded programming because it was faster than other languages. But Rust offered a cost-free way of ensuring memory safety, and it also offered usage of high-level programming features with system-level performance. I could talk about Rust for hours, but I had to keep it short because I have 12 minutes. Then here's Prust. It's a software implemented with Rust language. As I said, it complies to PUS-C. It was tested on VST 104, and it aims to be reliable, fast, and maintenance cost efficient. PUS-C packets in Rust, it implements the data structures to send, receive, and interpret PUS-C space packets. Has servers 1, 3, and 8 data structures in it from PUS-C. And their definitions are on the next slide, and it's basically a representation of PUS-C packets in Rust. Here are the definitions. There's serves 8, it has one request and executes the function defined by the user by giving the name of the function. Here's request verification. It has 9 responses, and each one of them indicates different states. For example, failure, success. There's housekeeping. It has plenty of TM and TC packets. It helps to report the peripheral connected to the devices. And it was partially implemented by myself. It wasn't fully implemented. Here is the hierarchical data structure of Prust, the telemetry and telecomat packets, which are abstracted well, in my opinion, and are compliant to PUS standards. So, okay, the test case, the setup, I used board 0, which Philip will talk tomorrow, and a programmer to deploy the Prust software. Here's the general overview of what our goal is. Here we have mission control, and we have our onboard computer. From mission control, we will send telecommands, and we will send responses from onboard computer, which we call telemetry. Example use case for servers 1 and 8. For example, on first step, let's say we say by sending TC81, we say execute function terminate from function arrays file with argument true. This function arrays file has a function table which is defined by the user, and it is so easy to add a new function. And you can see here some of the functions, and we indicate one of them in this packet. And on the second step, we will evaluate the packet, and we will get the function from the function table and execute and report the return value or how it went, how the execution went as a telemetry as TM17, which is service 1's specification. So another use case is housekeeping. For example, let's say we have these parameters. We can observe, monitor. We have the structures and it's empty. We by TC31 command we can mean, for example, create a structure of parameters which includes number 1 and 2 and set the structure ID to 0. We want to create a structure here with parameters 1 and 2, and then we will evaluate this packet and create the structure here, and also respond about how this execution went. And here you can see the structure is created, and after that, okay, the structure is created, but we want to monitor it periodically. Then we will send a comment to which indicates, we can send a comment which indicates enable periodic collection of structure ID 0 and report it periodically, and it will evaluate it, and it will enable the timer, and it will also look at the structures list, and it will report periodically the values in these parameters. And there are some next steps for Prust, because it's an ongoing project. Here's what we can do. We can check by API ID, read flash and FRAM device types, and UID, read temperature from onboard sensors, set the clock speed, at new test cases for each new feature, and also we should look into Rust-based RTOS for embedded developing, and we should propose and implement the migration of existing code onto RTOS kernel. If you are interested in contributing or any suggestions, you can email Jose by this mail, and you can check out the repository here from GitHub. And if you have any questions, make sure you ask about anything. Thank you.
Okay, great. So you even finished before this 12 minutes. And in fact, you took 8.5, so that leaves more time for discussion. Very good.
Yeah.
Also, yeah, your co-authors are Jose Feitirinha and Philip Gaib, who will be there tomorrow, and Jose is here. And before we start with the questioning, I also like to introduce Nicoletta, who is not here. She was supposed to be the runner, but unfortunately she could not. So, luckily Fernando joined, and he is going to support me in this session.
Yeah.
All right.
Actually, Artur, I'm monitoring also the YouTube channel in case there is any question. I will let you know, Artur. Okay.
Okay. Very good. Maybe someone already has a question. You can write this here in the chat. You can also write some feedback.
Yes, if you don't mind. Am I unmuted?
Yes.
Oh, hello. My name is Kirill. Sorry, I don't have a web camera. I work with guys on a PUS-C project. Maybe you heard about it. And we are implementing the PUS, the library, which also does the PUS standard in C. And so at some point we came to a question about how we want to verify what we are doing. Basically, we also and content decode the packets in several service types, but like how do we test that what we are doing will be properly received, on the ground station? And at some point we came to a discussion when we thought, hey, maybe we contact some other project, like, you know, your project, and we try to somehow establish this test case in which we try to send packets from our library and try to decode them in your library and backwards, so that we, you know, use it as our test framework. How do you feel about it?
Maybe I can also say something here. So, first question, you said TU Darmstadt, right?
Yes, Darmstadt.
Okay. So we also gave you a VST 104 board, right? Are you developing on that board?
Not right now.
Okay. So
not me personally. Maybe my colleagues are here who can tell more.
Okay. So what I can say is, if you develop on that board, Selman, he didn't put it in the presentation, but he did actually, like I say, a mini test tool, which you can like send commands. So you have a command line, and it's like a shell to access the satellite. And I mean, it all works over UART, and you can basically send some commands. So in principle, if you use our tool, you should get the same behaviors if both implementations do exactly the same. So this could be a start point. I'm not sure if someone wants to add something.
No.
All right, this sounds actually good. Guys, if you are here from Tutsat, do we have this board?
I'm sure you have, because
Yeah.
we donated one.
Yeah. It's just that he's not in Darmstadt. That's yeah. Working remotely also. This year is everything remote. That's currently the problem. But maybe we can set up a web client so he can access it over the internet.
Okay.
All right. Nice. We will figure it out. Thanks.
Okay, Artur, we have a few questions from YouTube. I have published them in the chat of the VVV.
Yeah. Please raise those.
Yes. So Paul Madel is asking is there an open source RTOS targeting Rust? And a second question from him is if there is an open source file systems implemented in Rust.
I mean, Salman, if you want to say something, you can join in.
Okay, I sent some links. I think they were from YouTube. There's Drone OS, and also OS sent me a thesis file. I think it was other RTOS targeting Rust. So I've sent some links there. Paul can look them up. And the question is there open? How to implement that? Are there libraries available in Prust? Yeah, there's a module, for example, for the PUS data structures. They are modularized well, and you can have a look at it from GitHub.
Okay. And also there is a last question from Paul that it says that if does PRUST support lower level protocols, example CCSDS, TypeKM, TC?
I mean, I don't really understand the question. I mean, you can send commands, and you can receive telemetry. All 4 services 1, 3, and 8, like someone presented. So you have housekeeping telemetry, you have command verification, and you can execute any random function on board. So we thought that this would be the basics one to show that you can, get started.
Okay.
I have a question. Did you present this to any ESA people or space industry people to see what they think about this? Because last time when I talked about a bigger aerospace company about using Python on a satellite, they were like, no way. I mean, they're not even using C++ because they cannot fully code test it. So how about Rust? Is this a bit different? Is it more low level then? Testable?
I wanted to, someone, you can say something afterwards, but I wanted to say something here. So it's not just like, I liked what someone put there, it's been the most loved language on Stack Overflow. But it's also a language which has been used, it's being used increasingly on the Linux kernel. So it's like, it's growing, and one of the reasons why it's growing is because when someone was doing the tools, at some point he said something which I found super interesting. He said, it took me hours to get it to compile, but when it finally compiled, it just worked. And that's normally the case with Rust. That was his words. I'm just quoting him. But I really like it because it kind of forces you to detail all of the things of the problem. You cannot just say, I want to convert a char to an int, and then and it works. You have to justify everything very well, or you have to, use the unsafe flag, and then you have to really know what you're doing. So if you try to follow the Rust way, it takes a long time to compile, and then it works. Someone correct me if I'm wrong, but I just wanted to add that because it was my input from you.
Yeah, that was really the case. Rust just enforces for you to just not to do stupid things, for like forgetting some pointers somewhere or using some null values. It just enforces in its compile time features. Yeah.
So I will not be able to do stupid things. Ah, too bad. That sounds like debugging before actually the program is running. Good. Interesting. Very interesting. Yeah, with this we go over to our next presentation. It's Andre, who's already here on the screen, and he will talk about the R2 Cloud and the R2 Server. So it seems like there's two separate components of this distributed ground station network system that he's developing. I would suggest to combine the name into R2D2 at some point. But yeah, I'm really interested to hear more about it. The abstract was a bit short, so I hope your talk is going to be a bit more enlightening. And the presentation is going to be loaded now. And then I hand over to you. Can you make yourself a moderator? No. Now you're presenter. So please go ahead.
All right. Thank you, Arthur. Okay. Next slide. All right. So hello, everyone. My name is Andre, and today I would like to talk on how to run open source project alone. I'm a professional software developer, 15 years of experience in enterprise world. And R2 Cloud is actually my hobby project, which I run myself for several years. And I don't want to give a lot of technical details on how it works and on the low level. I'd like to spend these 12 minutes on maybe high level design key points, which prove to be working, some not. So, and share this experience with you. So, a couple of words about the project. So, yes, as you find out, yeah, the R2 Cloud and R2 Server is a part of a client-server architecture distributed project, and this is distributed ground station network. The R2 Cloud is a client and R2 Server is server. So simple. The R2 Cloud is a fully autonomous and application and can run independently from the server side. And it can do several things. For example, schedule satellite observations and record the AQ data from a satellite. Then it can demodulate data, decode the data, and it can provide an interface, web interface, where you can look at the data and the API, Prust API, which you can use to download the data and do some analysis maybe. And optionally, it can upload the data to the central server called auto server. It's not necessary, but uploading to the server can provide some benefits. So currently, with auto server, you can actually gather observations from several base stations into the single web interface. So it's much easier to look at the results from several stations. And you can store the observations for some time, pretty long time. And also you can share the data with the community. So data shared can be shared with setnogs, FanCube warehouses, AMSAT-LM, HATU-Weather, and many other projects. So the single telemetry data can be sent to several projects which are interested in it. And initially, actually, I didn't plan to have a server side, central server side. I thought AutoCloud was supposed to work on Raspberry Pi in some rural areas and controlled remotely from the web interface. And as it turned out, this doesn't work really well, mostly because default memory card is very limited, so you can store unlimited amount of observations. And even if you buy a bigger card or some external USB hard drive, then it still will be limited. Well, with the central server, you can actually upload the data and store the data in some central blob service like Amazon S3. For a long time, it's very cheap. So that makes perfect sense. And secondly, the remote locations doesn't have Wi-Fi. So you have to set up some GSM module which can connect to the internet. But with GSM, you can't configure port forwarding and you can't really access remote location from your home and easily. Yeah, it is possible, but it's not like plug and play thing which you can install in the wood and just forget for a year. So a bit complicated. And thirdly, if you use a central server, you can minimize the traffic. So if you have a GSM modem, you can upload the data, upload observation only once to the server, and the server can distribute it between the interested parties. So that makes sense. Yeah, so there I decided to have central server. During the life cycle of a project, some key features were added or removed. The design principles stayed the same, and I'd like to go over them in details maybe because they have interesting story. So the key design principles are open source, KISS principle, tests, and automation. So the open source. AutoCloud is my hobby project, and I haven't had any experience in digital signal processing or satellite communications before. So it was good for me to have somebody who can review it. And the only way to share the code is share it with as bigger community as possible. So that's why I chose open source as a primary reason. The second reason is tooling, because a lot of services, they provide the services for free for open source projects. And several years ago, it was GitHub, Travis, and Sonar Cloud. They covered all my needs, and they are still really good at running my projects and my infrastructure. The second principle is keep it super simple, I would say. Again, when you run a hobby project, you're very passionate about it. You want to add as much as possible features, and because they're really cool, and especially when you run something like RTL-SDR, where you have access to all radio waves, and you can get a lot of kind of information. But it turned out it's not possible to make all features with the same quality. So it's very important to focus on one single primary goal of a project. So, and the primary goal can be defined as a single sentence which describes your project precisely. And if it doesn't, then something needs to be changed about it. For example, R2Cloud is a project R2Cloud is a station for decoding satellite data. That's it. So that's why initially I supported airplane tracking and air balloons, etc. But I dropped that support because of the single primary goal. And that was a really good idea, because I had to cut off a lot of functionality which was not really needed. And that's why maybe R2Cloud won't support audio communication with ISS, right? Because even the ISS is some artificial thing. It's not a real satellite, and I can't really decode the data. That's why only a very limited but very fixed set of features it will support. The next principle is tests. So when you work on a project over the years, you add more and more features. And more features will require more and more testing and making sure that every single feature works well. And I'm the only developer in R2Cloud, and I simply don't have time. And that's why I can afford manual testing. So I spent a lot of time doing automation, and it proved really working well. I can add more and more features continually and not breaking the old ones. This is very important. And the complicated software require complicated features. Another biggest design principle is automation, and that's generally a good idea for any kind of project. But when you are low on resources and maybe run a big project with a small group, that's a must-have. So, for example, in R2Cloud, I don't have any specific version of the application. When I'm commit into the GitHub will notify Travis, and Travis will run the tests, checks everything works, and if everything works, then nothing can stop me from releasing it. So I'm very confident that, okay, I can release it. And then Travis will publish the artifacts onto apt repository, where every client can actually download and install it. Yeah, so that's about automation and maybe generic principles. And these principles work really well during these years, and they help me adjust my target state of a project and focus on real important things. During the last year, I added at least 50 satellites alone. So I was able to download the data, acquire the data, and decode the data and upload it. The number of stations is constantly growing over time. So I think it's really good. So other people think that it works and they can install it. And I have my own 2 base stations deployed. They're very simple, Raspberry Pi, Discone antenna. But with these 2 stations, I was able to get into top 50 of SatNox contributors. And I think that's a good achievement. because I'm really testing things, make sure that decoding works, and I got these results. So I think everything works fine here. Yeah, so I guess this is it. I'm ready for questions, and I'll be available in the virtual hangout at the end of the day for informal discussion. So thank you very much. Thank you for listening.
Andre, very, very good, very nice, and totally on time. My God, you really have rehearsed it. Cool. Yeah. So, Fernando, do you have questions on the channels?
If you don't mind, may I ask
No,
here?
so far no.
Go ahead.
Very nice. So it's Kirill again. Hello, Andrei. I'm new to this satellite communications, and I was wondering in the decoding part of the project. I can imagine that the modulation is quite generic, like all satellites do it the same way. But I have a feeling that all satellites encode data differently. Like the guys from the previous presentation, they, for example, use this PUS protocols. So when you're decoding, you kind of need to know that they use this. How do you know how to decode?
That's a tricky question. Because some satellites, they send frames in a generic format. For example, X.25 protocol frames. In that case, I will just get the binary data and upload it. Some satellites provide the internal structure of their messages of their telemetry, like solar panels, voltage, and bus voltage, etc. And for these satellites, I can get these byte array and create a JSON document with all the structures and the formats. The number of such satellites much smaller than the total overall satellites. That's the reality. But still, yeah, you have to do decoding for each individual satellite, and it might take time.
Okay.
So, for example, as you know, we are now working with this TUTSAT satellite, and we will also use PUS stack protocol of a stack of protocols, including PUS and some TM frames. If we, for example, want to have decoding support by your project, how can we do that? Like I contact you and we share the details. How do we do that?
So I'm not really familiar with PUS. I've never heard about that before. So currently I support X.25 framing, and then X100 framing, and then CSP CubeSat space protocol frames. So if your satellite is able to send them, then you don't need to actually do anything else apart from just adding entries that NORAD ID these, the TLE these, and you got the data. If you got some weird framing, non-standard one, we have to develop it from scratch and add support across all the stacks. Yeah.
I see. All right. Thank you.
Okay, Andrei, I have a question coming from YouTube, but it's asking which are the project goals for 2021?
The project goals. Well, as for 2020, the primary goal is to add more satellites. That's never-ending story. Satellites burning up, they constantly launching, so it's never-ending story. The second thing is to ease the addition of the new satellites. So currently I have to do a couple of releases of R2 Cloud and R2 Server. Everything is automated, but it still takes some time. So ideally I would improve that thing. And as always, I'm trying to optimize demodulators, because the generic demodulators doesn't really work well, because the satellite is always moving, they tumble in, they can there are a lot of noise around, so there's never-ending story about optimizing demodulators. So I guess these three key things for 2021 is a top priority for me.
There's also the question, you talked a lot about the R2 Cloud, and we see the GitHub repository. How about the server part? Where do I find that one?
That's closed source, and mostly because yes, but it takes some time. So there's some reasons, and they're really good reasons to make it closed. First thing, if you're running an open source project, you're spending a lot of time making it secure, making it structured properly, etc., etc. If it's closed source, I can be more free in the way how I do some things and just don't care about them.
So you say the code is crap, the server part, and you don't want to show it.
I can share it. I don't think anyone would.
We have this discussion all over. I mean, we have this basically every year, that people, if it's really the reason that you say that you're afraid that it doesn't look good, or it's not working, or it's not up to standards, I say, I mean, just the people will contribute, and they will improve it for you if you let them do it.
Yeah, but yeah, that's the thing. It's partially the code, and partially that I'd like to focus on R2 Cloud. So, for example, I'd like people to come and contribute to R2 Cloud and improve the satellites, the modulators, etc., rather than working on the server side, because server side is very simple, really simple, and the protocol between the R2 Cloud and R2 Server is open, so you can go and implement yourself.
Okay. Okay.
No problem.
I sense some hidden agenda there, but maybe one last question from Fabian, because then we have to go to the next presentation.
I've seen that you provide very support much of the new satellites in the last year. So because you are using the J radio, you have to do the whole work of writing the decoders yourself. And by this, you have to do the same what is also done in GR Satnox for Satnox decoders, and also with the same what Diane Estavis is doing for GR satellites. Do you think we can find a way to collaborate on this part? I've seen your testing is really good, and for J radio you mentioned the automated testing, and you have always unit tests for all satellites. So this is a part where your contribution is really great in comparison to others.
Yeah, I would really love to merge our some decoders and just have a quick, maybe open discussion on how to do it properly. Because currently the G radio is, call me from the old ages, but I prefer a very simple thing. Right, read the beat and just pass everything beat by beat, rather than provide some weird structures of how to pass the data. We can work it out how it can be shared and maybe improved. Yeah.
I know also about a lightweight library instead of GNU Radio, and I have a lot of other questions. So I'm really looking forward to see you in the virtual hangout, and then we can discuss more. And yeah. And with this, now we go to the, thank you, Andre. We go to the next presentation. That's Kronos. I have to upload it. It's not there yet. Comes in late, but it's there. Uploading. And this Kronos project. Well, it's the time of the year that the year is ending and New Year is coming. So there's going to be New Year's firework. So let's talk about rockets, right? So
Yes,
Thanos
exactly.
here. Thanos, he will. He's the team leader of the student team called White Noise.
Yes, exactly.
Interesting name. Maybe you can also then explain where this comes from. He's an undergraduate at Technical University of Athens. And yeah, he's going to show us how to open source build our fireworks.
We hope that it won't become a firework. We hope that it will fly. Anyway, so my name is Thanos Patsas. I am the team leader of the student team White Noise. And I'm going to present you our last project. Is called Kronos. It's a completely SRAD and open source sounding rocket. SRAD means student researched and designed. And we borrowed that term from the competition that we're attending next year. We're going to the Spaceport America Cup, Intercollegiate Rocket Engineering competition. And among others, it splits the competitors into two big subcategories, SRAD versus COTS. COTS being commercial of the self and SRAD being student researched and designed. So we developed the rocket under the auspices of Libre Space Foundation. So some words about our propulsion system. It's not like a firework, because the firework, you have an engine, you light it up and it goes. Ours, it has valves, oxidizers, and run tanks, etc. So we have a solid fuel inside the combustion chamber burning. We feed it with oxidizer, liquid nitrous oxide in our case, from the external run tank shown in the photo. Here you can see the Mark I engine that we designed. So some general details about Kronos. It's going to reach an apogee of 3 kilometers, a max velocity of 0.86 Mach, a max acceleration of 10.3 Gs, and it weighs 30 kilograms wet with all the propellants and all of that stuff, and dry 23.32 kilograms. As I mentioned before, it utilizes nitrous oxide and paraffin as oxidizer and fuel respectively, 5.68 kilograms of N2O, and 1 kilogram of paraffin. So the M3000 Mark II is the engine that will fly eventually with Kronos. It weighs 9.36 kilograms. It uses paraffin and N2O, and it is estimated to produce 3,000 newtons of thrust for 3 seconds. Here you can see the CAD photos from the run tank that we designed and manufactured, the PCS, as we call it, the pressure control system, which is the coupler between the run tank and the engine compartment. But it also houses all the plumbing system of the rocket. You can see 2 ball valves with 2 servos that are actuated when the time comes. So the right picture is the actual engine itself with the fuel grain inside. You can see the injector orifices. I will have a close-up view in the next slide, and the rocket engine's nozzle. So these are the close-up views that I mentioned before. You can see the injector with the tiny orifices. The orifices serve the purpose to atomize the liquid nitrous oxide coming from the run tank in order to react better with the fuel and in order to burn the fuel. Actually, in the middle, it's the plumbing system, but a more close view. And the nozzle assembly. The nozzle is made from graphite because it can resist high temperature and stuff, and a cut version of the whole propulsion system assembled. So Kronos will be able to lift 4 kilograms of a 3U CubeSat format payload and deploy it when it reaches apogee of 3 kilometers, as I mentioned before. But we need to recover the rocket. We cannot land it propulsively, not yet at least. So we need to eject 2 parachutes as well as the payload. So in order to eject the parachutes and the payload, we made and designed a recovery system using CO2 cartridges. When the time comes, the flight PC gives a signal to 2 DC motors. The DC motors are actuated. The CO2 cartridges are pushed up. They're getting pierced, and the piston rises, throwing everything outside. The flight computer is made in a PQ9 format. We use the standard format that you all know, I think, from the Libre Space Foundation. So we use these formats too for our development. And now this is the recovery system made and tested. The middle one is a photo from a high-speed photo during a test. You cannot see the piston system there, but we just needed to test if the CO2 cartridges are actually punctured. So that was the reason we preferred to do this test. Now to the fun and interesting part. That's our rocket. So in order to have a scale, it has a diameter of 14 centimeters and a length of 3.7 meters. So you can clearly see at the top that we have carbon fiber structures. We designed them and manufactured them at the Hackerspace here in Athens. So you can see the nose cone with a metal tip. The body tube, it's made from carbon fiber tube also. And the fins are from carbon fiber too, except for the middle section that we have acrylic, because we have the avionics bay there that I presented to you earlier, and carbon fiber tubes with RF signals do not go hand by hand. So we need to have another medium to pass through, so we have acrylic. The cut version in the middle, you can see starting from right to left, you can see the propulsion again, the engine, the PCS, the tank, then the recovery system, then the main parachute with its lines, the drogue parachute with its lines again, and the 3 U-cubes at the format payload right below the nose cone. The third picture is from a program that we use to simulate the rocket's trajectory. It's called OpenRocket, and that's the CAD translated to weight components in order to simulate the trajectory. The slide is not working. Yeah, so these are close-up views of the whole assembly. Again, at the left, you can see the propulsion system, the engine, etc., with the fins. The middle one is a configuration that the rocket will have when it's vertical on the latch band before launch. We need, by the safety regulations of the common sense that we have, to load the rocket empty, of course, because it's not good to load the rocket with 55 bars of pressurized oxidizer. So we need to fill it. In order to do that, we have the PCS, we have 4 carbon fiber plates that are removable in order to access the quick release line that we connect to the external run tank. And then when the time comes, we begin with the fill procedure, disconnect the quick line, place the igniter in the engine, put the carbon fiber plates back and be ready for launch. And at the right, you can see a cross-cut version of the nose cone. We have a metal tip because it must withstand all the aerodynamic forces and pressures on the top of the rocket. But we don't want the outer carbon fiber cell to support the actual weight of the metal tip. So we put a carbon fiber rod in the middle, so the cell can only withstand the aerodynamic stresses during flight. So now, as far as the simulations go, you can see the logo of Fusion 360 with a closed source program. Follow me through, it will make sense, I promise. Kronos started as a non-open source project. Okay, we are just a student team. We were like, okay, we'll make our project and everything will be fine. However, after some months, we came in contact with Libre Space Foundation. That, as I mentioned, the rocket is developed under the auspices of LSF, and we took the open source ideology along with the project. So we had to transition from closed source programs to open source. So from MATLAB to Octave, etc. However, a lot of work was already done in order to change the CAD software. So unfortunately, we had to stick with Fusion 360. However, we upload all of our files in the GitLab in step format so everyone can access them. And also we use FreeCAD for every simulation that we do. We run a finite element analysis, vibrational analysis, CFD analysis in FreeCAD, and everything works fine. I can verify it. When learning FreeCAD, we had to test first in SolidWorks and other closed programs that we already knew from the school to test, and it was perfect. So you can see that we use Excel sheets in order to simulate basic calculations, so we can avoid doing everything by hand, like calculating shear stresses of bolts and stuff. Octave, because we transitioned from MATLAB, of course, for more advanced simulations. And of course, our favorite OpenRocket to simulate trajectories. It's the best thing ever. So these are some photos from the finite element analysis we run with FreeCAD. You can see the coupler. That's the coupler that is around the PCS, as you saw before. And the same coupler is used in the recovery system. We use the same part twice. So we designed one. It was fully over-engineered. It had a safety factor of 8, I think, or something like that. We ran finite element analysis. It was over-engineered, so we redesigned it and came with a second coupler that you can see on your right. You already saw it before in the CAD with a safety factor of 3. We verified the results of FreeCAD. They were accurate. They were completely accurate. And moving on, it's another simulation of the CFD of our noise cone. Now you might ask why you put only the nose cone, because it has drags and stuff. Doesn't it completely mess up your whole simulation? Yes and no. Yes, because it takes a lot of iterations to run. in order to calculate the wake drag and all of that stuff shown there with blue. However, we only wanted to see how the flow separates from the contour of the nozzle, and the wake drag is far enough that it doesn't mess with the flow separation. You can see the flow separation with a red, a little orange part. That's where the flow separates. So that's with FreeCAD. Again, it's verified with other programs that we already knew before starting, and it's completely accurate, as I mentioned before. Now, that's the Open Rocket. We love it. It's one of the best easy systems to simulate model rocket trajectories. We have a hard time simulating with Open Rocket because we have a hybrid system, which means that we have to simulate the mass loss of our run tank, not only the engines. However, we managed to do that with a dummy motor, as we call it. It's a motor that produces zero thrust, but it has the mass flow. And you can see a table at the bottom which says results max values. That's from an Excel trajectory calculator that we made when we didn't know the aerodynamic packet of the rocket. So we just wanted to see how much thrust should our engine produce in order to lift so many kilograms up. You can see it's pretty close. Of course, it's not accurate, but it's pretty close with Open Rocket simulation. However, the Open Rockets are a lot better results. So some cool photos to close. That's the test stand that we designed. We need to verify that the engine actually produces the thrust that we need. We do this with this contraption right there. We want to have both of the tanks vertical, and the external tank and the tank that will fly with the rocket, because we needed to simulate the actual fill procedures of the whole process. And conveniently enough, the vertical part of the test stand was used to drill the holes on the run tank, the vertical holes. You can see in the third picture there, the run tank is supported at the background. It was really convenient that this happened. It served the purpose of the drilling jig, you can say. And some more cool random photos. You can see the injector orifice there, the Rev1 and the Rev2, the control box, the run tank of the third photo with the recovery system and the plumbing system, and the internal parts of the Mark I engine that we designed at the right. So that's what I have to present about our project. I hope you liked our rocket. Okay, I already see questions on the public chat. Should I just answer?
Yeah, well, first, Thanos, that was great. That's amazing. And I always envy people who have such braveness to work with rockets. My experience with rockets is there was this water rocket with a Coca-Cola bottle.
Okay.
They put like, I don't know, 2 bars in it. Then this thing went up, and at one point it came down, and everyone was running because there was no parachute on it. And that's already this. I was so afraid, to get hit by a rocket. So and there was not even fire in it. There was actually just water. So, yeah,
I can understand.
Let's open the floor to questions. Fernando, you take over.
Yeah, we have a question from from Sojan that he's asking, how do you pump the oxidized engine?
So that's a really good question, because you would assume that we would have a separate pressure tank in order to pump it. However, N2O has a really, really amazing property of self-pressurization, which means because the N2O has a really low triple point, when with the appropriate temperature, of course, you can make it self-pressurized by the container, by the dimensions of the container. So if you have, let's say that you have, with a magical reason, a completely empty tank filled only with liquid nitrous oxide, without water, without air or anything. If you have a compartment empty, the nitrous oxide will evaporate with a steady rate in order to keep this empty part of the container at exactly 55 bars. So we calculate inside our run tank how much oxidizer will get evaporated in order to have the steady pressure, and we add it to the propellant's weight again. So the 5.68 kilograms that I presented are calculated with the added oxidizer that needs to be evaporated in order to keep the steady pressure. So that's how the pressure, that's how we pump the N2O into the combustion chamber. It's just the N2O's properties. It's amazing.
Okay. Thanks. Okay. A lot of people congratulating your work in the YouTube channel.
Oh, thank you. Okay, I see another question in the public chat. Simulation
Yes.
files, any documentation operators? Yeah, you can find a repository under the LSF repo. It's Kronos Rocket. We upload all the CAD files, all the simulation files, the result, everything. If something is not uploaded yet, it's because the Mark II closed the design 2 days ago. So yeah, we must tidy it up a bit and then upload it. But everything is under the LSF repo, Kronos Rocket. You will find it. And we use the CERN OHL license for every hardware component that we use.
Okay, do we have another question on the channels?
Not so far.
Otherwise, I was wondering, because it's a student project, and I mean, you need some incentive to keep the students motivated and running this project. Is there some support from your university in this regards?
So it's the bare minimum, we could say. We need some documents for the competition. They sign the documents and off we go. We have some exceptions of some teachers because they are good people and they want to help us. However, it's mostly done by ourselves. We don't have a lot of support. Like you can imagine that we don't work at our university. Our lab is the hackerspace. We don't have a lab in the university because no one gives us a lab or something. So why stick there?
Okay, sounds familiar. We also did build a CubeSat, and first the professors, they were like, "No way, you cannot do that, and we don't support you." And that changed completely towards the end.
Yeah.
So keep going.
Thank you.
And thanks for this nice presentation.
Thank you very much.
And yeah, so we go over to our next presentation. It's Anita. Fernando, can you grab the, can you be presenter and start the presentation?
Okay, 1 second. I become presenter.
So Anita Berni, she leads the strategy and execution at KISP Space. And we know her from very well from last year. She was running a workshop. And she's going to also present, talk a bit about this and the results and how to continue and build up upon this. She's really focused on space systems and the knowledge about it, and to make this accessible to everyone. She was director at Surrey Satellite Technology, and she is currently a member also of the board of directors of AAC Clyde Space. I don't know what's Clyde Space. But she's also, and that's, my God, I mean, if you have this in your CV, she's honorary group captain in Royal Air Force 601 Squadron. So everyone, be careful. And KISP, they're developing the world's first open source microsatellite platform. So yeah, she's totally into open source, and hand over now to her. Fernando, did you manage it?
No,
uploading?
Yes, I have some troubles to put it in the screen. Sorry. I have
Do you see
upload.
it? Anita, you need to unmute. I see you only connected with the headphones, so you should go to also check your microphone. Okay, Fernando, I do it, yeah?
Yeah, because I'm trying to set it, but I cannot.
So here it is.
Okay, thank you. Sorry.
So Anita, now you're muted.
Excellent. I think I'm with you now.
Good,
Hi.
very good.
I have a number of children competing for Wi-Fi and bandwidth. So I may turn my camera off at some point, but it's really lovely to be with you virtually this time rather than in Athens. It was a fantastic conference last year. So I'm hoping that I can give you an overview, as you say, Arta, of some of the results that we've had this year and some of the activities that we've been working on as well. 12 minutes isn't very long, so I'm going to be talking very much at the top level, and I hope that it's lots of questions and that you will contact me afterwards, and we can continue the discussion in the chat as well. We at KISP and at the Open Source Satellite Programme, we believe that open source space is going to be the next major disruptor for the space industry, and that the teams who are participating in this workshop this weekend are really going to play a strong role in creating that future. So I'm going to present a snapshot of that ecosystem and also seek your thoughts and ideas. Right, how do I fast forward on here?
Sorry, I have forgot to make you a presenter. So now.
Oh, perfect, thank you. Loading. So here's what I'm going to be sharing today. A quick look at what got us to where we are today, starting almost 30 years ago, would you believe, and how the open source domain and the space domain have converged. I'll talk about a little bit of what we talked about last year in Athens, and then I'm going to share an illustration that I've created of what the open source space landscape looks like. And then before turning to the discussion part of the talk, I'm going to share some updates on some of our activities over the past year. So in order to consider how open source and space can complement one another and create new space missions, it's really interesting to look back and to trace the parallel histories of these areas of development and see how similar constraints led to their inception, and see how the environments and the ecosystems and communities that they stimulated are creating the environment for open source space systems today. So back in the 1980s, we saw the very first flights of the modern microsatellites, and that was out of the University of Surrey here in the UK. And in the 80s, we also saw the first modern computers in the home, and that might seem like a really, you know, innocuous thing and a rather trivial thing, but it's really important because people used to have to go and book time on massive mainframe computers, physically go to where the computers were and load up their code. And to be able to do that from the comfort of your own home or from a regular office was really the start of how we were able to work more remotely and more collaboratively. And then in the 1990s, we saw a gradual increase in experimental demonstration missions in space. And we also saw on the open source software side of things, the software movement was starting to develop. Because of the restrictions that were imposed by commercial companies at the time, they wanted strict access, they didn't want anyone to change anything, it was never very good. So that's how the open source software community really began. And two great examples are Linux and MySQL, and they underpin many of our phones and a lot of the functions that we have today in a lot of our technologies. And then moving to the 2000s, we saw small sats transitioning from the academic and the scientific and experimental domain into commercial missions, and we gained a lot of wider industry acceptance, but they were still quite large as far as spacecraft go when we think about CubeSats, and quite expensive to launch because mass equals cost. And so the team out of Cowley and Stanford University developed the 10 by 10 by 10 centimeter sister way of making experimental training spacecraft, and that really ignited the start of the CubeSat revolution. And at the same time, this is when it really started to get interesting, because you started to get GitHub, GitLab, a lot of big data storage, data processing coming through from the open source side as well. So you can see these two areas, two domains starting to get much closely entwined. And then in the 2000s, we saw commercial CubeSats, small, really small spacecraft offering commercial capability. And that was really, really novel. And alongside that, you saw the maker community. So you started to see Arduinos, Raspberry Pis, SparkFun and Adafruit, making electronics really accessible for anyone to use. It didn't matter what your background was. You could tinker around, you could experiment, you could try and fail quite quickly and quite cheaply as well. And that's led us now to the 2020s, where we're seeing the first open source mission results from teams who are presenting this weekend. And teams are coming together, linking open source software, open source hardware, and bringing that to the space domain. And this is really where we see the future going and being disruptor for the future of the space industry. And so that really brings us to the present day. Here are a few photos from last year and the workshop that I ran with my colleague, Dr. John Paffett, who's the founder of KISP Space and also the initiator of the open source satellite program. And we ran an interactive workshop to seek the inputs of the participants about the teams that are active in the open source space community today. And we all went totally crazy with the post-it notes, and we came back with loads of paperwork, which we managed to distill down into the following chart, which is a bit of an eye test to look at quickly today, but please do have a look at it. Anyone who's seeing this chart can see their names, see their logos on here. If your names aren't on here, I need to know, because I know this is complete, it's just a snapshot. But what I want to be able to do is, with everyone's contributions and inputs, improve this and build upon it, and use this as a way to show the maturity of the ecosystem, and to identify where gaps exist, where we've got key strengths, and how we can work more closely together. The open source space ecosystem, it's really developed in a similar way to the development of terrestrial open source applications and services, and it really reflects a number of activities that are active in each of the segments. And the segments with the most participation and maturity are those where the software is really the enabler. And some of the first catalysts for open source space came from the imagery domain, where free satellite data acted as the catalyst for lots of different applications and services. And you had modeling and simulation tools that were starting to come out of the closed source into the open source domain as well, which made it a lot easier to leverage all of this great data generated and being offered on the free market. And then you had NASA and ESA as well, who were making satellite imagery more available from their in-orbit assets, that was stimulating this great use of all this data that's out there and finding new ways to use it, and also stimulating ideas for new missions. And then from the hardware perspective, it was more about looking at the ground stations to begin with, rather than the in-orbit assets. And that's something that we started to see change over the past few years with some of the missions that teams here are working on as well. And so we've seen that the convergence of open source and space coming together is creating this fantastic catalyst for novel and non-traditional approaches to delivering space and space-enabled systems. But what we think needs to happen now is, we need to build that momentum more, grow this ecosystem so that there's sufficient critical mass of capability across the value chain to enable the delivery of more missions and applications and programs. So before I turn over to the Q&A session, I wanted to share some of the developments that we've been working on in the past year. So just a reminder what the Open Source Satellite Program is all about. Our objective is to develop the world's first open source microsatellite platform. In order for space to be truly democratized, we feel it's really important to create an order of magnitude improvement in price performance, and that's why we're looking at a microsatellite. And of course, CubeSats definitely have their place, and SATs also will have their place in this overall space ecosystem. So here's a picture of some of the work we're doing at the moment. We're in the last few days, actually, I think we might have concluded this week, our first radiation testing campaign on 3 candidate COTS microprocessors. So low cost, fully robust, which is what we're going to find out during the testing, of decent performance microprocessors that we can use the basis for the platform processor in the open source microsatellite platform. We've just been awarded a contract to do the next phase of work, which is to prepare for proton testing so that we can determine their performance against single event upsets. And we will be releasing all of these results out into the community. A lot of the testing that's done on processors and other devices is usually held within organizations and institutions. We feel it's really important to share this information so that we can use that as a basis for stimulating more missions. And one more set of snapshots, really. So we've got a number of software and systems activities underway. We're trying to find out, you know, in a similar way to Andre, trying to figure out the best way to release this out into the community. So we've got GitHub repositories. We've also got a number of channels on Teams as well. And we're really loving the Kanban function within Teams so that we can progress our activities through their workflows as well and see how things are going. It's a really great tool. So people who are collaborating with us, they've got access to these, but they're still, you know, within a relatively close community. So we're trying to figure out the best way to open those up to a wider audience. So if you do want to see, get in touch and we can get you onto those channels. So that was a really quick run through, very top level. Do ask me questions. I'd love to talk more. And so just to move into the discussion section, which is really around the ecosystem. Well, a couple of questions I wanted to ask based on everyone's experience, you know, which segments and capabilities are the ones that we need to focus on developing more? You know, where are the gaps? Which additional areas of capability need to be included to make sure that we have a well-structured, mature, complete value chain ecosystem? Who is from this map? Whose logos have I missed that I need to include and make sure that we're promoting the open source space community? And just a basic one at the end. Have I categorized this in the right way? Are there better ways of defining where people sit in the ecosystem? So those are some questions to get the conversation started. Over to you guys. Thank you.
Thank you, Anita. Thank you very much. Yeah, actually, we already have one question. Pieros is shouting out regarding not that there might be people or companies missing logos, but rather the opposite, that there might be too many that do not really adhere to the open source principles. Maybe you want to say something to that?
Yep. So very good question. Everyone has a slightly different definition of open source. That is true. But it's interesting you mentioned cost. When we met with them, I think it was a year ago now at IAC, they've actually got some amazing work that they're doing on the payload side. Admittedly, I haven't been onto their repository to have a look at it, but they were talking about being able to release some of their information they're doing on the payloads. So that's a really good question. I agree. Not everyone sees open source in the same way, but I think that we need to start somewhere. And that, I think the end objective has to be, how do we make space more affordable and accessible? And sometimes tools and the underlying capability may not necessarily be open source, but they're accessible because they're at a sufficiently affordable price that they help to stimulate other things to happen. So it is a total grey area here, I know, but that's what I love about this debate, because I think everyone in this conference has possibly got a slightly different definition of what open source means. I need to include a few asterisks or maybe different way of denoting those teams where they're not fully open source but have some elements that they want to share.
Okay. Yeah, Fernando.
Yeah, we have a question from YouTube, from Axenov, that he's asking if are you using agile approach for designing and development or more a waterfall approach?
And again, I mean, it's a case of one size doesn't fit all. I mean, some things work better as an agile approach, and some of the activities we're working on with our collaborators are definitely following that really rapid iterative approach to just something, trying it and moving on quickly. Others where we have, from our experience, we have maybe a more mature starting point for our thinking, then it maybe makes more sense to take a waterfall approach. But I think there's not really a one size fits all. You have to think about what you want to get out of it, what your starting point is, and use this as your drivers for which approach suits you best.
Okay, thanks. We have also one question from the attendees, from Damien.
Yeah, hi Anita, thanks for the great presentation. Just to, as you are asking, are there alternative ways of categorization? One thing I was thinking is you may know the Gartner Magic Quadrant presentations, which are showing maturity as well as execution capability and all, because in your current visualization, you're putting basically everything on the same foot and saying you're putting either at the same level as, well, I'd say other things. And maybe it could be interesting to show something more nuanced in terms of where are they in terms of ID or vision versus actual execution. And it could be applied to open source saying, okay, at this stage, they have just published a few IDs, or actually the full documentation is available. And this would enable maybe to better visualize what is actually open source, to answer one of the questions, what is really open source as per the open source definition, and what is ongoing or going to open source?
That is a really good question, and it's something I struggled with as I was thinking, how can I put just simple snapshot that's easy to understand together? And I was thinking maybe I can do a heat map representation of some of that as well. I love the quadrant idea. I mean, I love a good two by two grid for defining lots of things. Maybe I need to do a 3D version of that. But yeah, I will definitely look at great comment, Damien.
Okay, I have also, I mean, my perception of this is, well, first of all, there's Sputniks in Russia. That's a company or an organization. They also want to build an open source microsatellite. That was my last information. Have you heard about those? So not Sputnik, but Sputniks.
Yeah. Yeah, I mean, they've recently understanding or awareness. I haven't been here yet, but I will definitely.
Okay, and my question was then, or perception is that, I mean, most of us here, I guess, we are doing some kind of grassroots development in our garage and building this sensor or this system. But I perceive that you're basically, from the, let's say, you're an industry player. You talk with other companies and you talk with the industry. I'm just interested in if you can report on their reaction, because I mean they live in the world of NDAs, ITAR, and confidentially. And if you say open source, what is their reaction?
It's interesting. I mean, talking to ESA, I mean, you guys know they're very supportive of new ways of trying to do things differently, and to find ways of bringing capability closer to people. So I think that they're probably one of the biggest challenges NASA. There are a few groups we're talking to at the moment who are really fascinated by the idea of developing what we're calling a next generation microsatellite platform, something that is performant and robust and flexible for the price or the cost of a CubeSat. And there are a lot of people who would like access to that capability, because at the moment business cases aren't able to close. It's just taking, it's all about timing. It's taking too long to develop a system to get to the point where it's ready to launch, and it costs too long to get there. And then once you launch the spacecraft, the lifetime of the mission is too short for you to make your money back. So the dynamics of the business case are working. So there are a lot of people who are really keen to have access to a design that will help them to short circuit that current blocker in getting to the point where they can have a commercial or sustainable mission. So there is actually a lot of interest, and we're we're working with a few teams to determine how best to structure involvement program. There are a number of different models that we're considering.
Okay, thanks again. With this, well, there will be the Hangout session later to talk maybe a bit more about this.
Thank you.
So thank you, and we go to our last presentation. Fernando, please take over to load it.
Yeah.
If you can.
Let's see. But I couldn't find the button. The presentation.
OLLO is the name.
Yes, Oyo.
Yes. However, I think that it's uploaded, but I don't know how to change it.
It is uploaded.
There's a okay. I do that quickly. So.
Okay.
And so our last speaker of the session is Alejandro, and but he's not alone. He submitted this abstract with a dozen other people. So probably half of the audience that is here in this room is co-author of this paper.
I don't think they are in this room, but they are watching the stream right now.
Okay,
so, yeah.
Very good. Yeah, and so it's a team of students from University of Vigo in Spain, and about 1 year ago, they developed small sets with educational purpose. And this one here, the project that they're going to present is called Oyo. So it's going to be your eye in the sky. And with this, I hand over to you, Alejandro, and I make you the presenter. Floor is yours.
Thank you. So, as Artur said, I'm Alejandro. I'm a team member in Ubico Space Lab, and I will talk about Oyo, the Open Little Luminary Observatory for short. So the agenda is this. I'll talk a little bit about the team, I'll present ourselves, and then I will talk about the Oyo mission, the requirements, and the challenges that a mission like this has. So, about the team. So, as Artur said, we are a team of students from the University of Vigo, from the different engineering schools of the university. That includes mechanical, electronics, telecommunication, aerospace, and some others. And our goal is to develop educational satellites to apply the skills that we have learned during our university years in a real project. And we have the support of several professors from different schools. There are Fernando Aguado, Fermín Navarro, and Arno Formella that have worked in previous missions, groups of the university like Chatcoveo, Lume1, HumeSat-D, and some other projects. And they help us guide and avoid making some glaring errors and things like that. So let's talk about the mission. So the Oyo mission is a space telescope that will be open for everyone, and the goal is to develop an open and interactive tool to take pictures of the sky and have a space telescope. So it will have 3 segments, like every regular CubeSat mission. The space segment will be the 3-unit CubeSat with a telescope payload on board. The ground segment will be composed of the ground station that we have in the University of Vigo, and a server from which everyone can access and request the observations. And the user segment will be you, to request the pictures, access them. They could be for fun, for research purpose, for divulgation, and everything in between. And here we have the concept of operations, how the mission will work. We have the satellite on board that has a scheduler, and according to the schedule, it will point the payload to a star or an object. It will take the picture and it will store it on board, and it will proceed to the next one, and that will repeat until it passes over the ground station. It will download the data, and the ground station will upload the schedule, the updated schedule. Once they are on the ground, the raw data of the images will be stored and will be accessible for everyone, but we can do additional processing to enhance the images or look for special details that we want. And also, as everyone will be able to download the raw data, they will do the same. And for the payload, we have some requirements. Due to the constraints of the CubeSat standard, the maximum aperture that we can fit it will be 80 millimeters, and we have a 3U, so we have to leave some room for the other subsystems. So the maximum size of the telescope will be 1.5U. With this allows a focal length of 100 millimeters or so. And for the sensor, we will use a CCD sensor, black and white, of 1.4 megapixels that will give us a reasonable balance of the angular resolution, field of view, and the weight of the image. So here you have the requirements table, which is a little bit, with this configuration, we will have an angular resolution of 13.3 arc seconds and a field of view of around 5 degrees. And we have a simulation of what the pictures we would like. We have an image that's courtesy of John Matthew Sadler in the middle of the objects M81 and M82 of the Messier catalog. And with some image editing tools, we have a simulation on top of the resolution that we will have with this telescope. And below we have an image of the field of view. That's a bit wider than the image. It's rotated, it's made in Stellarium, which is an astronomy open source tool. And this is what we expect we can make with this telescope. The main challenge of this telescope, of course, is the pointing, the ADCS subsystem. In Earth observation, this is still a problem, but not as hard. But here, as we have long exposures, because the objects are very faint, we need long exposures up to 5 minutes. And while we are doing the exposure, we need to have very accurate stability, because if at the start of the exposure we have a point that's in the middle of 1 pixel of the CCD, if the light from that object will fall randomly in an area that's the stability that we have of the CubeSat, so we can have motion blur. So to avoid this, the pointing stability has to be ideally equal or even less than the angular resolution that we have in the pixel. So as I said before, we have an angular resolution of 13.3 arc seconds, which means we need a pointing stability higher than that, so around 10 arc seconds during the full exposure of 5 minutes. This means that we have a pointing requirement that's very strong, and we need better sensors than that and good actuators and we need, of course, a 3-axis stability during that point. For the pointing accuracy, it's not as hard, but the hard requirement is set by the stability. But we have a target, that's the Andromeda Galaxy. That's a very big object. It's almost 5 degrees of angular size. So we have a pointing accuracy requirement of 0.1 degree. That's very strong. This is the main challenge of this project. So because they are almost state-of-the-art pointing requirements, and this is the main challenge. But we have some others. We have made a small review of open source ADCS systems that are being developed right now. One is UPSat from LibreSpace, and the other is a CubeSat that has made another tag right before this one in the other room from ASAT team from Greece. And they are somewhat similar in their configuration. For the sensors, they have 3-axis gyroscopes, magnetometers, sun trackers, and GPS. This is generally good for most missions, but for OYO, the resolution, the sensor accuracy that we need is very strong. So we will need either a star tracker, which is a very hard to develop system, which is very complicated, or a combination of sensors that's good enough so they cancel each other's errors out, and we have a good accuracy at all times. For the actuators, they use magnet torques and reaction wheels. We will need at least 3-axis reaction wheels for the stability. For the slew maneuvers and for pointing the satellite, we can use magnet torques, and we can use them also to desaturate the reaction wheels. But during the exposure, we need the reaction wheels to be operating. So that's one of the main challenges of the ADCS. As I said, we have other challenges as well, like, for example, the data rate. That's a a single image will weigh around 12 megabits without compression, and this will limit the data rate, will limit the amount of pictures that we can take each day. So with UHF band transceiver, we will, they usually have, they are very common in CubeSat, but they usually have tens or maybe 100 kilobits per second. That's not enough for our requirements. That will enable us to download maybe 1-2 pictures each day. So the satellite will be mostly idle during its mission. So we will need at least an S-band transmitter with maybe 1 megabit per second of download. That will enable us to download much more pictures and to have the satellite working harder and taking much more pictures every day. Another challenge, but a smaller challenge, is the power budget. That's always a challenge in CubeSats. But in a 3U, we can generate up to 8-10 watts of peak power with solar body mount panels. If that's not enough, we can consider the deployables to increase the amount of power that we have and increase the science resolution of the mission, the amount of science that we can generate. And that's a little bit of the least challenges of the mission. As I said before, the main challenge is the ADCS subsystem. I think that's all that I have today. So thank you so much for your attention. And just as an acknowledgement, this conference has been selected by the European Space Agency's Academy to participate in the concurrent engineering workshop that will take place next year. So that's all for my. Thank you so much.
Thank you, Alejandro. Very good. So you even left a few minutes more over for questions, and I'm sure there's going to be a number of questions. So Fernando, please take over.
We have a question from YouTube. That is the one that is written now. That is from Aman Narula. He's asking, is there a redundancy strategy that you have implemented in case of one of the reaction wheels has a problem, has a malfunction?
We haven't defined the complete IDCS system architecture yet, so we have built it more with the requirements. And the minimum that we require is 3 reaction wheels, but we can configure and maybe being 4 on board, so we have some redundancy. The idea that we have with our 3U and the 1.5U telescope is to leave enough room for the ADCS subsystem to have as much freedom to reach these requirements.
Perfect. Okay. Also, we have another question here from our chat that from Michael Cadolias, that he's asking, congratulations for your work, and then he's asking which will be the orbit that you are aiming for your project.
Yeah, the good thing about a space telescope, different with an Earth observation mission, is that we don't kind of care what orbit this is, if it's low Earth orbit or synchronous. Everyone can work. What we have to do is to configure the scheduler so that we don't try to watch an object through the eclipse of the Earth. So that will be Earth observation instead of space observation. So most orbits can work for this mission.
Okay, so this is a question. If you select, depending on the orbit and the altitude, if you go very high, do you think that you about the orbiting strategy or not?
If we go higher, the size of the Earth will be smaller, so we have more range, so more objects that we can observe at any time. But we also have longer link distance, so that's something that we have to balance, because we want the higher data rate possible to generate more pictures.
No, okay, actually, I was thinking more for the end of life of the mission, if you were considering the orbiting strategy.
No, actually no, because we wouldn't have a propulsion of board or anything like that.
But we have a couple of questions more in the one from Jose Manuel Diez that I want to ask a question in voice. Okay, so then go ahead, Jose. Okay, otherwise I read it. It's
Microphone is not working.
maybe not. So I in my here in the chat is, have you considered using fluid dynamics actuators instead of reaction wheels as your ADCS actuators?
As we said, as I said, we haven't defined the architecture of the ADCS subsystem yet, so we are open to the possibility. So thank you for the information. We'll explore it because it seems very interesting. And yeah, the main action is the reaction wheels because it's what we know and it's the most documented actuator. But yeah, we will take a look at that. Thank you.
He's mentioning that he will give a talk tomorrow on this topic, so maybe you're interested in. Also, I have a question on my side that more in operational point of view. You mentioned that you expect to receive requests from users. Have you already started to consider how you will operate on these aspects? So you have a planning system for observations, or will be based on artificial intelligence on board, or will be on ground, that you have someone that will schedule all the observations? How you want to deal with this?
Yeah, in principle, we will have a first come, first serve system, but because we predict that a system like this maybe will have a lot of demand, we were thinking about setting slots, so public slots that will work first come, first serve, and some additional slot that can be justified, like we maybe have a form and explain why you want to serve this mission, and maybe have a selection procedure, and also a special slotting for maybe some one-off astronomical events that cannot be observed at one period, so we can. That is interesting, so we can select a slot for that, reserve it some way, and maybe have open slots for everyone and some more dedicated science slots. We haven't decided some very specific measures, but it will work something like that.
Okay. Thanks for information. We have more questions. I don't know if we will have time for all of them. Another one channel. It's about the. Okay, I read it because I haven't had time yet to read it. It's from your picture. It looks like that you were not using UHF at all, only S-band. At the same time, you would like to schedule more observations. Does that work out in terms of power and energy budget?
Yeah, ideally, our strategy will be use UHFs for general telemetry and telecommand uploading, and the S-band will be used for data downloading, so with a higher data rate. That will be our main idea. And for the power budget, as I said, we think that with body-mounted panels, the power budget will be okay. But if we need more power, we can add deployables, so with more solar panels, so we can balance everything out.
Okay.
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 Fernando, I guess we stop here because we don't want to miss the break. Alejandro, thank you very much.
Yeah, as a final remark, because we didn't include it in the presentation, our website is ubiquospacelab.space. So if everyone, I will write it in the chat. So if you want to visit and take a look. So thank you so much.
Okay. So let's do a small recap of the session. It was the first session, and so we discussed, or what was presented is we have a payload, a telescope. We also have links to the open source ecosystem that we can use to build a satellite. We have defined the communication system, PUS-based for telecommand and telemetry. Also on the ground segment side, we have a distributed ground network, and moreover, we even have a rocket. So now it's just a matter of putting all these things together, and then you have your open source space mission. Thanks very much to everyone. We're going now into the break. That will be from now until 4:10, and we will meet in room 1 for the lightning talks. And here in room 2, we will continue only afterwards. That's at for the demo session, and that's at 4:45. So that's in 45 minutes from now. Yeah, hope to see you there. Or there's also the other tutorial, so it's you to decide. Okay, see you for the lightning talks after the break. Ciao. Fernando, when you leave the session, don't end the meeting, just do the lockout.
What I'm doing, Arthur, I don't know why I couldn't change the presentation. I was trying to find out the button.
Okay, that's okay. We discuss later.
Okay.
There's a small green button.
Where? Because I'm like I cannot find it. Which area?
You upload a presentation.
Yeah, okay, when I go to the
there's 3 buttons next to the trash can.
Okay.
You can activate and select the presentation.
Okay.
Okay, let's have a break.
Okay, perfect. I will check it and I see you. Okay. Okay. Yeah, I see it. Perfect. Thanks.
So, hello. Fernando, this is gonna be 30 minutes. It's gonna be really. Pierre was saying there's no sound. Well, no speaking so far, right? Now there should be sound.
Yeah, I can hear you well.
I think on the YouTube.
Okay, sorry.
Okay. So what we're going to do is a live hacking. So the whole idea is that you join me in hacking, and the best setup for you would be if you have 2 monitors. So one where you can follow, and the other one where you actually type the thing in and create the projects on your computer. If you only have 1 monitor, you can do as well, but then everything is a bit small maybe. So I give you just a quick introduction about this CCSDS file delivery protocol. In a nutshell, it's like FTP for space. So file delivery, sending of files from ground to the satellite, and also the other way around to receive files from the satellite. So you might wonder, my God, what's the big deal about sending files to a satellite? And in fact, this standard is 20 years old, but it's only actually now that this thing is being implemented and that we move from packet-based to file-based operations. So ESA and NASA, they are now adopting the CFTP protocol more and more. And initially, you see here on the left side, we operate on packets. So we send, if we want to send, let's say, an onboard computer image there, then so software updates, we split this into small packets and send this up. And the same for the download. If we have larger image data, it's all sent into packets. But this protocol was never actually, there's a service for this, but it was never really designed for that, to transfer a larger data. And that's why there's the CFTP protocol that basically makes sure that you can do this in an automated way. Of course, the same thing, a large file is being split into smaller fragments, but the whole process of getting and retransmitting this file, if segments are being lost, this is all automated and part of the protocol. So what we did is to, here's a link to the standard, so you can read about it. What we did is we implement a Python library for a Python module for this. And we also implemented a GUI to make it easier than to, this looks like a file explorer or like a FileZilla. And we have also a chat channel for this. So I hope you get, with this tutorial, you get an interest in this project, and you may try it out and maybe join us even. That would be great. So for this example, I have here the scenario that the intention is to set up the mission control system, and we send a file to a remote rover. The rover actually acts as a server because it's waiting for files. So it's listening on a port, and the mission control system is the client because it's using the service to send a file to this remote rover. So with this, I close this presentation and I start start the screen sharing. And already I feel like half an hour is not enough time for this. So when you follow, the first thing you do is create a folder somewhere. FTP demo, maybe. And of course it lands on the other screen, but you have it here. Anyway, just give it any random name. And now we create a folder for the rover. And we create a folder for mission control. Okay. So just to make clear where we are. Either we are in the mission control, open new window, or the rover. And we start with the rover. So we open a shell here, and we clone the project. And I send you here on this, on the left here in the public chat, you see the link to the repository. And what we do is we clone this. So git clone. Yep, then it goes there. So we see here in the rover folder, we have this Python CFTP module. And what we're going to do is in this module, you see also there's example folder, and we're going to use one of these examples. And this example makes use of this Python module that we have developed. So we need to install this module. The way I like to do it is not to install it system-wide. So I like to use a virtual environment, virtual env. I write it also in the chat. There's also the other way to do this, Python m venv, and then the name of the. So that would be equivalent, but it's just easier. So virtual env, and then the name of the directory. I call it venv. So the whole idea here is that you generate this this directory is being generated, and all the modules we're going to install then later, they will end up in this directory rather than in your system directory. And this works the same on Linux as on Windows. Yeah, and I would hope you can get this started. So either you use the virtual env venv or the Python m venv, and then you need to supply the folder name, and I call the folder venv. Now we need to activate this virtual environment. Okay. Maybe I should go a bit slower for people to follow also, because I realized that it's really easy to talk fast, but typing is usually a bit slow. So to activate this on Linux, you use the dot operator. By the way, is this somewhat clear? Yeah, dot operator, and then venv. Use the tab to autocomplete. So venv bin activate. So this command will activate my virtual environment, as you can see here. Okay. I'm going. Yeah, and on Windows, the command looks different. You need to go in the shell and use this. You run this activate.bat, which is in venv scripts activate. But I'm not giving any further support now for Windows users. So we focus on Linux with the syntax. So if you do a pip list, you see it's empty. You have your pip, you have setup tools and wheels. So you have a clean Python environment. And by the way, of course, I expect all of you to be on Python 3. Yeah. So this is active. You can see it here. Now I'm going into this. Well, I need to install this module that we have here. So I mean, the easiest way is I just enter it. And as a setup file, that means it's a module. So I can install it, pip install, and I just use the dot for this current directory. And it's being installed. Which when you do pip list. Okay, maybe it would help if someone also types this command here in the chat. echoes my commands, so maybe this will help some others. You can see that this library is installed, and also there was a dependency bit array, which is also being installed. So one more thing, because it's an optional feature, because I mean the files are being sent using the CFTP protocol, but they have to go over some communication network eventually. Or I mean the whole use case would be to go over the radio channel and to use CCSDS frames. You could even use AX25 frames if you want. But we are working here locally in the computer, and so we can either use UDP protocol or 0MQ, ZMQ. So we use that one. If you want to use that one, then you type install 0MQ, but you don't have to. We can rely on UDP. That's that is available to anyone anyways. So you don't need to use install ZMQ, but you can. So the rover side, we have installed this module. Now we go into this examples folder. And oops, we see a number of files here. We see the a number of files called example, and then there's a server file. And we're going to run now the server file by Python server. And it asks us which protocol to use. If you have not installed 0MQ, it will give you a warning here. But yeah, so we're going to use, in this case, UDP. We press 2, press enter, and then it says it's running, and press enter to stop. So if we would press enter here, it would stop. So the server is running. The rover is waiting now for files. So let's go over to the mission control, and we do basically exactly the same step. We open a terminal here. We clone the same repository, right? And then we have the repository here. So it's so far it's identical. We create a virtual environment. And we activate the virtual environment. Maybe someone in the chat can give me a feedback. I hope really people are following this live and start hacking. And if you can give me a short feedback if I'm too fast or if I'm too slow.
Arthur, we have a question from Paul Madel from YouTube that he's asking you if the protocol, the CFDP implementation supports class 1 and class 2 CFDP.
Good question. So class 1 is unacknowledged, meaning it will send the file segments and the PDUs or the protocol data units. It will send it out without knowing if they ever arrived. That's by the way why we use this UDP protocol. So basically, class 1 is unacknowledged, sending out. You don't know if it arrives. Class 2 is acknowledged, and that means there must be some feedback. So that the sender knows, okay, the file did arrive completely, or maybe just a few frames are missing, and then it will resend it. So far, it's only a class 1 implementation that we have done. Supposedly, that's the easy part. Was still a lot to do, but now the next step would be to implement this class 2, and that's why you're here. That we're happy to have you to join us in this activity.
Yeah, and one last question. There's also a question from YouTube that is asking if with the software can you simulate that there are some packet loss in the link?
Actually, good point. So far, we did not explicitly test this, so as a test case, no. Yeah, that would be interesting, of course, to test if what happens if something is lost. But as I say, we are using the class 1.
Yeah.
And what we would see is that on the receiver side, it would just be aborted. The file would be discarded. So I activate the virtual environment on the mission control side. Now I do the same thing. I go into this module and I install it. Pip install dot. I can verify it with pip list. It's there. And so again, it's identical so far. Now comes the difference. I go into the example folder. And I'm going to run one of these examples, which is the send file. I'm sending a single file. By the way, at this time, I did not install the CRMQ, so there's a small warning. But we're using this UDP. And OK. So what we see on the, we get some debug messages here. So on the sender side, there's not so much. Actually, it's a small file. So what we see here is that the transaction was started. There's an indication that it started. Then it also says that the end of file PDU was sent. So it sent the file. We don't get any more information. It starts the transaction, but it doesn't give us information about the ongoing process. It just tells us that the end was reached. So the end of file PDU was sent. And then finally, transaction is finished. So from the sender side, from the mission control, we have sent the file, and we hope it's at the rover side. Here at the rover, we have a lot more messages, but that's also because this message here below, this is meta. These are so-called file store operations that we have put in addition to this example. They don't have anything to do with the file sending itself. I will explain this in a second. So the important part is here. So the rover received metadata. Metadata is the first PDU. PDU means just a protocol data unit. It's like a frame. It has a header. This header is fixed. I mean, the length, but the content is different to define if it's a metadata or if it's a file PDU. And then it contains the data. So that might be the file data. So this PDU arrived. It's a metadata, and it tells the receiver. So it tells the rover that, look, I'm going to send you a file now. It has this name and it has this size. And so expect some more PDUs coming in. In fact, it will receive one PDU because it's a small file. It can fit in one PDU. If we make a larger file, you will receive more of those indications. So for each file segment that you receive. And then you also receive the end of file PDU. And then the rover knows the transfer is complete. And then it checks if actually the length of the file that was declared in the metadata is really matching the file size that was received. Because it's unreliable transfer. So you might have lost some PDUs on the way for a larger file. And then this would be the point for the rover to know, oh, the file was not received correctly, so I discard the entire file. So that's the result then of this class 1, that the whole thing would be discarded. So this was a successful transfer. There's other examples there. What I'm going to do now is to look into the code a bit and browse with you through the code to explain a bit more in more detail what actually happened here. And we're just looking now at the two files. Make this a bit bigger. So here on the right part is the server, so that's what's running on the rover. On the left side is what's running on the mission control system. You can see for a large part it's quite identical. Let's look at the server side. We have we use the CFTP module. Here we choose the technology for the transfer, either CRMQ or UDP. And then we create a config object. And basically this one defines our setup. And that's an important point, that before you start sending files from rover to mission control and so on, you need to define what is what. So it's not for spontaneous clients joining this network and sending files. So you know in advance who's taking part in your in this transfer, who's in this network, because you need to know the IP of those players, of these entities, and you need to know their entity ID.
Okay.
So this is something that you need to configure beforehand. At least that's also foreseen by the standard. So if we can make this a bit more ad hoc or flexible, this may be something that we can look into. But for now, the standard says that you should know that you have your mission control system and you want to control your rover. And that's what we... Yep.
Sorry, we have a question from YouTube that they are asking how this protocol knows the server that the file transfer has been wrong. So if there is a CRC system to identify that the transmission was wrong, or how is done this?
Say again, how does the...
Which is the mechanism to identify that a file has to be discarded? So if there is a CRC thing...
There's also a CRC, yes. And there's a couple of checks, but the most important ones are the CRC and also the file length. So, and this is defined in the metadata PDU. And so the receiver side compares between what is supposed to, what is expecting, and what actually was received. Okay, sorry. So on the server side, we have to define in this config object, we have to define the local entity. That's in this case the rover. So that's the entity running the file, running this thing. So that would be, I would give it an ID. So it would be 1. That's the rover. And here's the IP localhost and a port. Make it easier, I have the same last number here. So that's the rover. So the local entity, that's myself. And then here's the remote entities that can connect to this rover. In this case, it's only 1, but it's a list with 1 entry, and it's ID number 2. And that's the mission control system. I also need to define where files are being saved. And I use a subfolder file server that you can, if you go into this rover directory, you see in this examples, there's a files folder, and that would be server. So this would be the files that the rover, that can be accessed on the rover. And here's the transport layer. And now comes the heart, which is the creation of the CFTP entity. You pass over the config object. And then on the rover side, you just bind to this port. And then it's listening for incoming files or for any other CFTP actions. And it's serving those. And you see, it's running until you stop it. And then it unbinds and shuts down. So everything else is handled by the protocol itself. And for this, you would have to look into the source code, which I encourage you to do. But it's all handled by the protocol. So creation of directories or receiving of files, this is then all done from the protocol. So it's very automatically. On the mission control system, we have here an example of sending a file. So this is a script that just runs once to send one single file. but normally you would not do it like this. You would implement this logic into a GUI, for example, so that when you click a button, send this file, that then this method is being called. And this is actually what we did with this GUI project, but I'm not going to show this now. That's going to be, will take too much time. But basically, it's a browser where you drag a file from the client to the server, so from mission control to rover, and then it triggers this action. So in this case, you see, I do a config object again. This time the local entity is 2 because this, it's the mission control system. It's the entity 2. These entity numbers have to be unique for each participant in this CFTP network. And then the rover, the remote entity, is 1. So you can see it's basically the mirrored version of this one. Same here. I put this in the files folder, subfolder client. Here's a bit different. So I create a CFTP entity. I want to start connecting to the remote host. Since I'm using UDP or CRMQ, I need to do call the connection of the transport and specify to which of these entities I want to connect, because there could be other rovers in my network that are listening for files. So here I tell, let's connect to entity 1. So this is needed so it knows the IP address to connect to. And then here comes the actual transfer. So it's a PUT request. So again, I have specified here the destination. Maybe that's a bit redundant, but just to make it clear, so I send to the rover, destination ID 1. I send a file called small, and I receive it as a small remote. We can actually also change this as a medium file, and you can also, if you leave this out, then it will just use the same name, which also makes sense. And here is the answer to the question. So we have only this unacknowledged mode that we are supporting so far. And here's some other stuff, which is basically some kind of meta operations that you can say that once this file delivery is successful executed, then run those requests. And this could be anything from creating a new directory, creating an empty file, removing a directory, etc. So all these operations that you expect to do on a file system. Yeah, I mean the whole mindset of the CFTP actually is that you're sending files from one entity, your local entity, to another entity. And the other thing is either some meta operations like fiddling with the file store on the other side, but there's nothing like a GET request as such. So in order to do a GET to download data, you would say you trigger a proxy operation. So you tell the rover, hey, rover, please send me a file. And then the rover initiates a PUT request to send a file from its local file system to the mission control. So the focus is really on sending us a file from yourself to someone else. So that's really the mindset of the CFTP protocol. And that makes it a bit easier then to understand, because you have to really focus only on this aspect, and everything else is just some meta operations that are actually quite easy to implement. Let's take out this file store request for now. And then, so I do this PUT request. I also take away this one here. I do a PUT, and then I wait for the thing to finish, because it's running in a thread. I need to know when it's complete. And then it disconnects. Okay, so let's run this test again. See the server, the rover is still listening. And this mission control has finished now. And when I run this again, okay, UDP. Of course, you need to be consistent. If you use UDP on the rover, you should do so on the mission control as well. And see, it's a larger file. So there's much more file segments that are being created and sent. and then in the end of file PDU was received and the transaction finished. Yeah, and basically that's the way to send files to a spacecraft. And just to mind you that it looks a bit like, wow, what's the big deal about this? But as a matter of fact, it's really only now that ESA, at least, I don't know much about NASA, but in ESA that we are adopting this. And for example, for the JUICE mission that goes to Jupiter, the downlink of science files is using CFTP. Of course, the acknowledged version of this, so class 2 receiver. And also Euclid is, I think they're doing both up and down link. And in general, it's moving towards file-based operations. So if you have a grasp of how the thing works, I think that makes a good on your CV if you intend to apply at a space agency like ESA or so. All right, my voice is gone. If you have questions, we can maybe have a quick 5 minutes or so.
Okay, so in the chat looks like that everything has been replied around your explanation. Otherwise, please write again any missing questions to be replied. Paul Mather just mentioned that he has an implementation in C about this protocol, and he would like to test it against your implementation, if possible. So probably we'll share in YouTube the link to his project.
That would be cool, some cross-testing, because it's it operates in UDP or some, I mean, this it's language agnostic. If you have a receiver talking UDP, CFTP, then potentially you should be able to communicate those systems together. Yeah.
Okay. There's a question in the element channel also, that is how will low quality communications channel impact and show up? I guess that is the file, no, so far?
Yeah, I mean, the CFTP protocol is really designed to meet the challenges of space link communication. So that is that you have a low a huge latency between the communication. So you have the light time that becomes effective when you send something to if you communicate with Mars, so satellites orbiting Mars. So that's also the big difference between FTP, where everything is instantaneous, and no matter if you're on the other side of the world, in a fraction of a second, you receive all the frames. And also the outage of communication, so that you might be uplinking stuff, but then you have no more communication with the satellite, and only maybe 5 or 10 hours later, you can continue the communication. So this protocol is really designed for this, for such cases. However, it's not designed to be a solution to really noisy channels. So it is expected that this lower level communication is made as reliable as possible. So it can work with frame loss, PDU loss, but then it will re-trigger it and re-trigger the sending. So if you have a really noisy channel, then even that protocol will not really work well.
Okay. Thanks, Artur. Another question we have: why are you using UDP versus TCP?
Yeah, we tried TCP first, but then we realized TCP is a connection-oriented protocol, and since we want to use we tested class 1, which is unacknowledged transmission, and we also want to actually at some point have frames that are missing. So we need to use a protocol that allows us to simulate more what actually would be the reality, which is to communicate over radio with a satellite, and where you might lose frames. And so UDP is connection, not connection oriented, and this is what we needed. And also it's much easier, by the way, to implement it. But that was just a nice side effect.
Okay, thank you.
Good. Then maybe, unless there's some other pressing questions, I mean, we can. I'm really happy to get your feedback over the chat channel, or you contact me. But I think now we should head over to the other session, which is about the CubeSat connector PC104. So I close my screen here. Okay, so I registered as the author for this next topic, but actually I hope this would be a really open discussion. And I can actually make, if anyone wants to grab the stage, then I can make them a moderator. The whole idea would be to discuss now about the PC104 connector, and maybe also more general about the board itself. Let me see. So maybe Milenko, do you want to start while I try to find some slides?
Yeah. So the reason why this discussion now basically exists is because a while ago Arthur and I think Jan from LibreCube project started defining the PC104 for LibreCube, and it's just a very basic draft of how it could look like on the wiki. And now people started using it, and we realized that we might have to add some more mandatory pins to make it possible to integrate different projects with each other. So currently, one thing that is a bit missing is an overview who is actually using it. And also, when developing the PCDU, some questions came up. And because there were a lot of discussions just in chats, I thought it would be a good idea to do it. Yeah, here Pira says they're using it also on the Satnox comms board, and there were a lot of private discussions, and the idea was to make these discussions public, to get everyone involved and also see who's using it. Yeah.
Also from my side, very interested. Hi, Arthur.
Fabian, it's you, yeah?
Yeah, it's me. Sorry.
Good. Hi.
Yeah, we're using it currently on the PCDU design, which is also from you. And we are using it on a onboard computer, but are not sure if we want to modify it. So would be very interested to have a common layout.
Does anyone has a picture of the PC104 connector? Maybe we can then load it here, and people can designate the connector.
I think you can open the for PC104. We have something, but we don't have the canvas on the corner. So we try to keep it, as you know, we try to keep it close to what you have. But I think you have like the canvas on the corner, and we moved it out. But we can also try to put it back if there is like a standard that everybody's following. I'll put the link on the chat.
So that would be that one. That's, wow, quite populated, right?
I mean, this is like how we started using it. We tried to keep it. We went also through a couple of other like ComSpace and other providers, and tried to come up with a common ground. But we know that it's not fully common. Some of the things I also tried like having some like a canvas on the corner. We just felt it didn't make too much sense, so we didn't do that. But I mean, we can use it as a basis for a discussion. I'm not saying that this is the way, just that this is what we have right now. If there are things that we should move, just to have, I mean, some of these things are legacy, as you see there. Others are completely optional, so you don't necessarily have to do it. Other ones are mandatory if you want to work with our OPC, which is also open source, of course.
And I know maybe Pieros has it somewhere or knows where it is from the Setnox comms.
Yeah,
they also have a quite populated connector, and that's where I saw that
putting it up, yes.
Yeah, that there's need for communication because of antenna deployment and stuff like this, which is mandatory on most CubeSats.
Let me pull it up, and I can send the link here.
I mean, in the meantime, so what we have put here is, let's maybe make it a bit bigger. It's really the bare minimum of definitions, and even there, I'm not so 100% sure if this is the best selection. So we were trying to find where do people mostly put the 5-volt line, where's the ground, where's the raw battery output. So this seems to be quite, let's say, de facto standardized. Because I think this is very critical to have the power lines. I mean, if you put the boards together, they should be at the same place. But for example, CAN bus, this was rather arbitrary to put it there. So there's these 2 pins for the low and high channel, and then there's also the redundant CAN bus. And this would be interesting to see what people would prefer to have it and where.
One quick question to Jose. The chart you have provided in the spreadsheet, these header H1 and header H2 are the connector rows we see on Arthur's screen right now, starting from left to right, basically.
Yes.
Okay, cool. Yeah, because I never looked at your chart, so just trying to figure out how this is documented.
Okay, I think Pieros is taking over.
No, Arthur, sorry, I did it by mistake. I give it back to you.
No, it's fine. And actually, if people can switch on their camera, it's nice to have more of a discussion feeling. So everyone here is invited. With 24 people in the room. Fabian, hi. And when you do so, put the light behind you. That's really the best, so that your face is completely dark and and have your microphone off, right? No.
Perfect. It's only the only light source in the room. Sorry. I mean, I can turn it off if you want. If that's better now. Oh no, my camera crashed. Nice. No, it's back.
It's better now, yeah. Good. Jose, what's flashing for you? Okay.
Just bring it along.
Okay, maybe also to raise that, I mean, the connector is an essential part, but in the end, it transports power and signals and data interface. And we are really into using the CAN because it's really reliable, and it also is kind of space grade because it's being used in space missions and it's low cost. But there's one big downside, which is power consumption, which is really something. So what we have observed is for the transmitter, it's about 20 milliampere that is being drawn in active. In inactive, I think, what was it, Milenko? Something like still 2 milliampere or so.
Yeah,
much
something
less, though.
like this. Yeah.
So the active part is the problem. And active is, you can do it that you only activate it when you actually send something. But so you could have just, let's say, the master node sending and switching on the transmitter at that time. But there must be at least one of the other parties in this network to acknowledge this frame that was sent. So there must be at least one other transmitter on to acknowledge the frames that were put on the bus. So we have to find a solution here, because otherwise we use all the power for the CAN bus and have no power left for the payloads.
Yeah, actually, we did 5 minutes ago. We ended a concurrent engineering workshop where we tried to figure out which components we can use for CubeSat. And one thing we totally forgot was the bus. So we haven't included our bus in our power budget currently. So that's not good. Thanks for reminding me, Arthur, even though you didn't know that. And there is some power left. Yeah, but we don't know. I have to see if it fits.
So what are the pins that you expect to have for sure?
On the connector?
Yes.
Good question. I don't know. Don't think we have a layout right now. We have 2 layouts for PC from the PCDU you provided basically, and the OBC we are developing. And this is brand new, so I don't know if we have a chart to share right now.
What I can say is that from our side, we'll try to make it compatible. I mean, we should try to reach something common. Yeah? At least, even if it won't, it should work together.
Okay, Piaos, I guess this is a typo. 2 lows. Can I low? Can I low?
There is Elias here, who is the the one that wrote it, so can probably answer on it.
Okay. And I see I2C is still there. So yeah, maybe what's your thought about I2C? Could this be used like as a backup to as a backup communication bus, or to communicate with the payload, for example?
I think that there's obviously, unfortunately, because many people are still poised to use it, right? And they already created things around I2C, like it might be a reasoning to stay there. But another thing would be, what is the minimal subcomponent that you could imagine, and if that includes a CAN bus driver on it, right? So if it's something like, for example, for the comms subsystem that we have here, we do have the antenna deploy and the antenna detect, right? And those are assigned, but in theory, those could be in the bus, right? But that means that the other side needs to be addressable and have a driver, and it's either going to be I2C or CAN bus, preferably, obviously. So I think that the only question here is, could we envision a reason of having I2C versus having a CAN bus, right? For a super minimal subsystem, like a part of a subsystem, right? Like really something that is somewhere else in your bus, and could use I2C.
I want just to add something more to the confusion. One of the links, I don't remember which one, but one of the links and the link that I sent, there is a part of for references, and back then Philip, which was the trainee doing the work, he looked into, there is a paper which, there was a paper which looked into multiple issues on multiple buses, so it's like single event effects and so on. And I think the most safe one was actually UART. And for VST 104, what we thought was the communication with the ground should come through the radio, could be done over UART simply because that is something. And then the main OPC could communicate using Canvas or something similar. It doesn't have to be like that, but that was what we thought, and that was the basis. I don't know which link it was, but I can try to find it.
Fabian, yeah.
Maybe.
Yeah, go on.
No, I think that Ilias can specify for the I2C that there was something around compatibility with existing antennas or something. That's what I allude to existing systems with I2C. Antenna deployment systems, I mean. Ilias,
it would be nice to have on the computer, though, be a high-speed communication protocol. Maybe have something receiving on the antenna, you can typically have your front end transmit the, like, let's say, constellation in the D constellations to bits. In other words, IF high-speed channel.
So that was obviously not going over a high-speed channel because I only got basically half of your comment. But yeah, that's actually the point. I think we have the two camps that we want, or the two aspects we have to consider. One is the things, the pins that should be mandatory for, or that will be mandatory for all missions, like an antenna deployment and a robust system bus, and also the 5-volt ground planes and so on, these connections. And then what you mentioned, Leonard, is to other optional buses or systems that that not every other system might support, but that at least we know that are located at those pins. I mean, in the end, we have 104 pins to allocate, and we should make sure that we know where to put this. And I think this is the whole of the challenge of this discussion here, is where can we centralize our efforts, and then later on make sure that everyone is adhering to the same standard. I put this with LibreCube. I've put this wiki page up, but I see that there's no way for others to edit it there. So it would be maybe nicer to have an online spreadsheet or something.
Or probably a repository that people can MR or something.
Or repository, yeah.
And probably also have like this discussion more frequently, something like a standardization body that we meet and discuss. Because frankly, like that's the speediest way to actually get up to speed on what's happening and who's doing what, right? And like right here among us, we have, I don't know, like 5 or 6 different developers and implementers, probably more, or prospective developers, definitely more. So maybe we need more of this.
Yeah, and the only reason why I was asking about that is because I kind of envision like one board, it'll be your front end, it has your LNAs and power amps, and then maybe your digitizers, and then you take that into, let's say, an IF stream or a digital stream, so you have raw samples going into a different board. That would be like let's say an FPGA board, and then you can have the FPGA board loader for different modulation schemes. You're basically taking your raw bits, making your constellation out of that, then decoding that, then sending that out on, let's say, like a CAN or IC bus. See what I'm saying? I mean, that was kind of my thinking behind the high-speed bus. It would essentially be your F of the front antenna.
Can I speak on the high-speed bus? Because the definition of what is a high-speed bus depends on your application, right? Like, if you're gonna go all the way to LVDS type of high-speed bus, or lower type of things. And the question that I would like to ask back to you on that is, or for all of us to discuss, is that most of the times those kind of things are dealt with within spacecrafts, are dealt with point-to-point connections, right? Like between two specific systems that require such a direct connection. And generally speaking, the 104 has this bus aspect to it, which is that you don't really care to have like point-to-point type of things, right? And when you do, it's kind of like secondary usage of the bus. Now, if we're going to be going down the road of assigning also possible point-to-point high-speed connections for the usages that you just said, which are totally valid, by the way, like IQ sharing or high-speed payload data sharing between the storage and the processor or whatever else it is, right? We need to be careful on the limitations of the connector itself. For example, LVDS, I'm pretty sure it's going to be almost too hard to go through such a connector, right? And it will depend on various factors, but it will be probably a mess. So, yeah, go ahead.
Okay, so our discussion, I think it's up to us to decide what we consider high speed, and then it's really going to be relative to the sample, bit rate. So you say if you're digitizing let's say constant, you're digitizing a certain bandwidth. That's limited in our applications, anyways, because this is mainly digitizing minutes of bandwidth. You're digitizing a lot less. And then in the connector that we have, there's a way to get around the entire bus structure where you like serpentine, from here to here to here. So you have this board-to-board connection, and then like the top board is connected to the next board over, let's say, two pins, and then that board is connected to the next board over 2 pins. So then there's a way to only have a serpentine one-to-one connection. I don't know if that makes sense, but it's just an idea,
Let me also bring in another point, which is the don't know if you're familiar or if you heard about this lean set activity. It's driven by Japanese professor, and they're actually focusing on generating ISO standards. They have done so in the past, and they have currently on their agenda to actually standardize this CubeSat connector. Let me just show you. I cannot share with you the document at this stage because I think it's not public. You can see here, this is the organization, and here you can find some public downloads. Well, actually, there's only one public download. The other one is all password protected. But you see the their goal is to make an ISO standard out of this. So I think it would make very much sense to get involved with them and see if they have ideas. I mean,
do you think that they could work in an open environment? Because by the website, it doesn't seem like it.
Well, the thing is, this standard in the end, will not be. It's an open standard, but it's not free of cost, as far as I understand these ISO standards. but they share their presentation. So eventually, if they standardize it, if it goes through, they will present this, because they also university, this UNISEC activity organization is involved a lot in this. University of Würzburg and so on. So they will promote this. So if we could find a way to kind of get our voice in, and I mean, in the end, it's just about to allocate the pins here on this headers. And if we can, if we see that this is a good allocation and it's even ISO standard, the better, right? And so far, it looks quite, I think they're quite correct. Is it something you're interested in to follow up?
I think now we are at a point where there are so many people starting to develop open source hardware that if we decide on something to use, maybe others will also use it, maybe also companies, because yeah, like someone mentioned here in the chat, like ISIS, GomSpace, ClydeSpace, they all have their own thing, but it's not compatible with each other. So if we decide something that is compatible across our projects, maybe at some point they will adapt it.
Yeah.
That's my point, because they will not create something like GomSpace will not create something that is compatible with ISIS boards. They will never do this, because you should buy all their stuff. So
on the other hand, we might consider that you know, you see now, let's take ASAT as an example. They're using part for LibreSpace, which probably will be, let's call it our standard, but they're also buying commercial components, and other teams will do the same. So I think we should aim a little bit into the direction that we find the best compatibility with also with commercial boards that are already available. It probably is not completely possible, as Dave has suggested, but I think we should keep that a view on that.
Proprietary boards, you mean, not commercial, right?
Sorry, say again?
What's that?
No, you said, completely agree with you, apart from the point about the other boards being commercial, they're proprietary boards. Our boards can be commercial too.
Yes, well, I was referring to commercial off the shelf, what you know, you buy from these suppliers as ISIS or GomSpace. And I think this was one of the original ideas where we started from, is to look, you know, what is the compatibility that we can, when we compare all of their layouts, what is the best compatibility that we can reach.
I had it apply if you can answer that. We have that's showing up right now. We got 5 volts input, and then also 3 volts. This is 28 volts. Where's this 5 volts coming from? Is that from solar cells, or is it, you know, solar panels, or and then which down, or is it coming from 28 volts?
Now, okay, maybe to shed some light on this assignment overall. That just means that you can expect either that your system puts those signals there, or it gets it from there. So if you're a power system, your job is then to put the 5 volt output on those pins, your 3.3 volt output on those pins if you support it, and ground on this. So you can imagine you have a power system developed, and it just like the one that I presented before, we support 5 volts, so that will be then there. If you also supply 3.3 volt, you find them there. And if you develop a onboard computer, you would know where to grab your 3.3 supply power from those pins. Of course, only once after you attach the power system. But that's the whole purpose of this assignment, that you as a subsystem developer, you know where you find your stuff, your pins, your communication lines, or the other way around, where you have to put them. Plus, and that's also part of this allocation, is to have some user-defined pins. So to have some areas where this is mission specific then. So you would have, let's say, systems off the shelf, and I use the same name, off the shelf, and it doesn't mean that so open source system can also be off the shelf. I think that's what we're working on. But the thing is to have then a common agreement that when you put this power system that this university has developed together with this attitude control system that this other open source company has developed, and you match this together, that this thing does not explode, and this is actually working, and that data can be exchanged and controlled. And also, the intention is not to think about different types of connectors, because when also we talk about high speed, the next suggestion usually is that people say, then let's skip this connector altogether. But the connector is there. It's there since, well, almost 20 years for the CubeSat world. It's there even longer for the PC104 world. So let's standardize this one and agree on these pins, on these lines, and continue from there. And yeah, I agree with Malenko that we should find a way, a repository or something, that we know that this is the up-to-date and this is the reference. And maybe we can then, if we don't agree with something, maybe we can then also or regularly have some work groups and iterate on this. But to have one central point where we can find this information. And if we manage to get others on board, like people who like to write ISO standards, or people who, just want to make use of these boards, then and have some ideas, what else to put in, then the better.
I think we have a starting point here, and Milenko, thanks for putting together the live spreadsheet here, so we can see the direct comparison of the three things that we have right now published, right? Like the VST104, the Satnux comms, and the LibreCube original definitions. And I think that we should do two things. One would be to come in here and do the work of reassignment, basically, like what needs to move around in order to have a common unblocking situation among us three. So that's especially between Satnux comms and VST104 in a sense of actual existing boards. The LibreCube standard can be more abstract, I guess, around it. And then that's the one work that needs to be done. And then the second work would be to go out and see what's the current compatibility with existing proprietary boards that are out there, right? And if there are like huge blockers, because of course there's going to be blockers, right? And there's going to be like things that are not compatible, catastrophically or not, critically or not, right? And we just need to identify them and see if it makes sense for us to have any compatibility with any of them. But I suppose that the first thing that we need to do is internally among the open source projects that are working right here, just figure out that we have the correct assignments among each other.
Good. I think that's a really good wrap up, and Konstantinos is going to add some more.
Yeah. I'd just like to say that it's going to be possibly a hard task to get also commercial, not commercial, proprietary manufacturers on board as well. So for example, there are companies without interface documents or datasheets online even. So we will need some some attempts to get data from there. However, I think there is indeed a good starting point, and many architectures, like for example, the last pins to be to contain the switched power lines. So maybe this can be also a good starting point. And we can start from the open source architectures and then move to the public proprietary ones, and then try to expand further.
Good point. We have to acknowledge, though, or remind, though, that for the closed source commercial, they actually make, I think, a bit of a living of adjusting and fixing those boards together because they're not compatible. So the incentive to be compatible, you can, I mean, look at the web browsers, then you see the whole situation. But yeah, so let's keep going in this direction. I think that's a very fruitful comments we had here. And let's all go to the room 1 for the conclusion, and then we have some
just a
PRs, yeah.
Timely wrap up so that we don't leave this hanging. I suppose that we should get it back with our teams, complete this spreadsheet that Milenko really rightfully put together, and then we can probably arrange for a call or something to, in 2 weeks from now or something, over the holidays, to figure out, next steps on this, at least for Among Us 3, right? So that we have those projects together. And the users of it. So Konstantinos, of course, because you're also developing your own board, right? So you should put your own columns here for your own board there.
Yeah, of course. I mean, we don't have anything huge, but yeah.
Still, cool.
Okay, nice. Then let's go to room 1. And then later have a drink.